Decide for yourself. Whether models are inherently useful. What if the tools we use to understand reality, those neat diagrams, perfect equations, and elegant models, are seldom actually true? What if their power comes not from what they are, but from how we are able to use them? That's the idea we're exploring today. Whether models are inherently useful. Let's start with the fact that models are generally approximations. Stories about the world told in the language of mathematics, lines, and symbols. And yet, these stories have changed everything. Take, for instance, one of the most iconic stories of them all, the Bohr model of the atom. It's simple, almost childlike. Tiny electrons orbiting a dense nucleus like planets around a sun. It's elegant, visual, and, oh, by the way, completely wrong. When Niels Bohr proposed this atomic model in 1913, it was revolutionary. It explained why hydrogen's light spectrum showed discrete lines, why energy came in packets, and why atoms didn't simply collapse. It also marked a turning point, the eventual bridge between classical physics and the coming quantum revolution. But soon, its flaws appeared. It couldn't handle atoms beyond hydrogen. It ignored relativity, and it failed under precise measurement. The model that had seemed so perfect was suddenly a stepping stone, a simplified fiction. And yet, it is still taught today. Why? Because within its narrow context, it's brilliantly useful. The Bohr atom introduces students to the idea of quantization, without drowning them in wave functions and probability fields. It's a ladder rung, one we later discard, but one we could never hope to climb without. Now, consider another model, perhaps the most influential of all, Newton's formulas of motion. The formula relating force, mass, and acceleration. The formula describing gravity as the attraction between objects. These equations built the modern world. For centuries, they explained everything from the fall of apples to the movement of planets. They powered the Industrial Revolution, guided engineers, and even sent rockets into space. But here's the twist. They're also wrong. Or rather, they're now better understood as useful approximations. At high speeds or near massive objects, Einstein's relativity replaces them. At quantum scales, they collapse entirely. The universe, it turns out, doesn't play by Newton's rules. It merely behaves as if it does within the range of our everyday experience. And that's the point. Models are not inherently useful because they are perfect, but that they are tools, lenses through which we can approximate truth. Their usefulness depends on context, on the domain, the purpose, and the questions we're asking. But this dependency doesn't make them weak. In fact, it's what makes them astonishingly powerful. The Bohr atom and Newton's formulas may both be wrong, yet each remains indispensable within its domain. Newton's equations still describe everything from baseballs to bridge designs with stunning accuracy. Bohr's atom still helps countless physics and chemistry students take their first steps toward quantum mechanics. And the main thing to remember is that models are inherently conditional. That their power emerges when human curiosity meets empirical reality. When we test, refine, and apply them judiciously. That their usefulness doesn't come from truth, but from their ability to work beautifully, reliably, and repeatedly within the contexts we care about. In that sense, the story comes full circle. Models are the fictions that make truth approachable, the scaffolding around which understanding grows. And while no single model captures the world as it truly is, together they form a web of insight so vast, so remarkably effective, that it continues to build our understanding of the universe. So, determine for yourself whether models are inherently useful and whether there is a place for them in the study of Zen.